Today we are continuing with our second talk. Here we have Ahmed Maghri. He is a first-year computer science student, and he's really excited to talk to us about the Qubit and Shor's quantum algorithm. So please.
So, hello everyone. As you said, I'm Maghri, computer science major. And today we're going to have exploration with Shor's algorithm. We're going to know what does it serve to, what does quantum have to do with this, and the most important part, how does it actually work? I'm going to give you now the answer for the first two questions. One, we use Shor's algorithm to break RSA encryption. Second, we need quantum computer to run Shor's algorithm. Now, just in this sentence, you already heard three words that would qualify by a bit scary, right? RSA, encryption, and quantum. So that you enjoy your journey with me, I'll have them to give you some foundations for cryptography and quantum computing. Let's start then by cryptography. Cryptography is formally defined by the mathematical study of techniques to protect data and information. And we mainly deal with it with two subjects, encryption and decryption, where encryption just means the way transforming data such that authorized parties are the only one who can understand it, and decryption is just to make data to its original state back. And RSA, just one of the most famous techniques for encryption that we use commonly. And to really understand how does RSA actually work, I think the best thing will just give you a quick small example. Take Alice and Bob. Alice and Bob are just two lovely friends that want to communicate with each other, but privately. And how they're going to do that? Let's say that Alice want to tell Bob, hey, how are you doing? What Alice and Bob going to do? They're both going to take two prime numbers. Let's call them P1, P2, P2, and P4. Then Alice and Bob are both going to compute the product of the two prime numbers. And it's going to give what we call a semi-prime number that we're going to call SP1 and SP2. And what Alice is going to do, she's going to hash her message in such a way she uses the SP2 of Bob. This, moreover, both Alice and Bob publish their semi-prime numbers. That's what we call public keys. But P1, P2, P2, and P4 are just known by their owners. And the way how Alice hashed her message is in such a way that she used SP2, and the only way to decrypt this message is that the receiver should know what were the two initial numbers that formed SP2. And since Bob is the only one who knows P2 and P4, he's going to be then the only one going to be able to decrypt the message. Now you might ask me, okay, Ahmed, but if P2 and P4 were, I don't know, 13 and 14, and then SP2 would be 143, even if it would take me some time, at some point, I would be able to actually find what were P2 and P4. And to answer to your question, to your remark, you're totally right. And that's why when we use RSA encryption, we usually use prime numbers that are approximately 200 digits, which gives semi-prime numbers that are around 600 digits. And even our most powerful supercomputer needs at least 24,000 years to factor out such a big semi-prime number. And that's why RSA is actually good. So you actually may notice that RSA relies on one big axiom. They state as follows. The time needed to factor out a big semi-prime number is really long enough to discourage anyone to try to find them. And actually, if you are somehow able to break this axiom, you should actually be able to break RSA. Remember this for later. Now, let's move for quantum computing. So, quantum states, who are they created? We all heard that quantum computers are built by qubits instead of bits. We also all heard that qubits can be in a state between 0 and 1, while bits must be either in 0 or 1. But we never actually understood how does that actually work. So let's discover what's happening behind the scenes. Let's say we have a quantum state x. X is described by two amplitudes that we call A and B. And how are they chosen? They're chosen in a way that if we measure x, we have a probability A to measure 0, A squared, and a probability B squared to measure 1. Meaning that if I measure x, I'm not able to know how much is in 0 or how much is in 1. I'm just able to measure either 1 or 0. However, with respect to some probability. And this is one state made by one qubit. If you had a state made by two qubits, I would have A00, B01, C10, D11, and so on and so forth. To understand even better, let's say that we have a state y. Y defined by 1/2 00, 1/2 01, 1/2 10, 1/2 11. If we would like to measure y, would actually have equal probability to measure either 0, 0, 0, 0, 1, 1, 0, 1, 1, since they all have a probability of 1/4 to be measured. Okay, now we understand theoretically how does quantum bits work. We would actually create a quantum qubit. Usually, in our classical computers, we used to create bits, so a 0 or 1 state, by using the presence or the absence of electricity. But unfortunately, we can't use the same system to measure to create a qubit. There is no between states between electricity being absent or present. There's no such a bit of electricity present. So we had to come up with a new way. And this new way would be choosing an electron. An electron has a special property that we call the spin. An electron could be pointing down, which then would represent the 0 state. Could be pointing up, which then would represent the 1 state. It could also be pointing somewhere in between, which then represents a state between 0 and 1. And that's actually what we call the phenomenon that we all heard of superposition. And how to create a quantum computer, take electrons, match with these electrons, make a register, make registers, you get your first quantum computer. Now that we have our foundations of cryptography and quantum computers, you could actually finally move to, I would say, the most interesting part. Literally, Shor's algorithm. Let's recall our previous axiom from before. The timing that you factor out a big semi-prime number is really long enough to discourage anyone to try to find them. As I said, if we're able to somehow break this axiom, we would be able to break RSA. And that's exactly what Shor's algorithm is trying to do. So let's see clearly his goal. Given a semi-prime number n, find the two prime numbers p1 and p2, so that p1 times p2 should be equal to n. People have tried to solve this problem before, obviously. However, we couldn't find an efficient algorithm. And our most common used way, just to pick a random number guess g, such as g would be smaller than n, and hopefully it should be either p1 or p2. This is not always efficient, right? So what Shor's algorithm trying to do is to take this bad guess g and to make it in a better guess, so that this new better guess would probably help us to find p1 and p2. So that would be our first step. Pick a random number g, so that g would be smaller than n and bigger than 1. Next, to continue talking about our algorithm, we'll actually need our really helpful term. It's essential to continue the algorithm. The term is stated as follows. Any two whole numbers a and b that are co-prime, and by co-prime, I just mean that they don't share any factors between them. There exists a power r in natural numbers and the multiple m, so that h power of r is equal to m times b plus 1. Equivalently, h power of r is equal to 1 modulo b. What does modulo b? It's just a fancy way to express the reminders. If we had, for example, x equal to y modulo z, just mean that if you take x and divide it by z, you get a remainder of y. And to even make it more clear, let's take an example. Let's say that we have 2, x is 2, and z is 5. 2 to the power of 1 would be equal to 2 modulo 5. 2 to the power of 2 would be equal to 4 modulo 5. 2 to the power of 3 would be equal to 8 modulo 5. However, it is bigger than 5, so we can actually use 8. 8 divided by 5 gives a remainder of 3. Since 8 is equal to 5 times 1 plus 3, then this becomes 3. And finally, 2 to the power of 4 is equal to 16 modulo 5. And again, 16 is bigger than 5, so we can reduce it. 16 divided by 5 gives a remainder of 1. So 16 is equal to 5 times 3 plus 1. Then this will become 1. You don't notice something? Actually, we have found the number r, so that 2 to the power of some r should be equal to 1 modulo 5. And in our case, r is 4. So why did I give you this term? What we are trying to do is to find an r so that g to the power of r is equal to 1 modulo n. So that g is again our random guess, and n is the number that we're trying to factor out. Then, why am I doing this? Take the one to the left. You get g to the power of r minus 1 is equal to 0 modulo n. Then, using our famous formula a plus b times a minus b is equal to a squared minus b squared, you could factor out our previous expression. And we get g to the power r half minus 1 times g to the power r half plus 1 is equal to 0 modulo n. Take some time at the end of the presentation. Take some time and look at the expression. Notice that we actually didn't find the numbers that we're searching for. We're searching for p1 times p2 should be equal to n. However, we find two numbers p1 prime and p2 prime such that the product is equal to a multiple of n. Since the remainder is 0, this must mean that the division by n gives a remainder of 0. And this makes sense, and that's why p1 prime times p2 prime would be equal to multiple of n. And what does that implicitly mean? It means that p1 prime and p2 prime share some factor with n. And moreover, since n just have exactly two factors that are p1 and p2, if we're able to somehow extract the shared factor between p1 prime and n or p2 prime and n, we would be able to find p1 or p2. And actually, we're able to use this to do this using a really cool algorithm that's called Euclid's algorithm. If you use Euclid's algorithm or A and B, you find the greatest common divisor of A and B. And since again, and just have two dividers that are P1 and P2, if you apply Euclid's algorithm or P1 prime and N, we'll get either P1 or P2. And it would have been the same if you applied P2 prime and N. And assuming, for example, that we found P1, it would have been enough to just compute N over P1, and we will find P2. And this will be the end of our algorithm. If we found P1, P2, that's P1 times P2 would be equal to N. Or maybe not. Why? You may actually feel that it was a bit too easy, in the sense where I just told you an algorithm is able to factor out a number N, a semi-prime number N. So how is RSA still efficient? So why do we still use RSA if RSA is actually breakable? Like I just told you an algorithm that could do it. Moreover, remember that I give you a whole talk about quantum computing. I didn't mention at all quantum computing at any point here. What could quantum computing would have been? Let's recall Shor's algorithm main steps. First, make a guess such as G is smaller than N that shares no factors with N. Second, find R so that G to the power of R is equal to M times N plus 1. Third, if R is even, calculate G to the power R half plus 1 and G to the power R half minus 1. If R is odd, go back to step 1. Because if R was odd, then R half will be not a whole number, G to the power R half wouldn't be a whole number, and we're searching for a whole number. This wouldn't make sense. And fourth, use Euclid's algorithm to find the greatest common divisor. Looking at all these steps, where could quantum computing would have implicitly been? It was actually in the second step. How did you actually find the number R? So I didn't talk about this at any point. And if we're just getting randomly a number R, what would have been better than our original way to just guess randomly P1, P2, and hopefully it's P1 or P2. And that's where the whole quantum subroutine comes. The whole quantum subroutine would be about finding R. We're going to try to make a quantum state where somehow we should be able to extract R. And to do this, we're going to need two quantum registers. Registers, again, just mean a bunch of qubits. First, a quantum register that has a size of 2n. And all the qubits should be exactly set to 0. Second, a second register that is exactly equal to 1, meaning that all the qubits are set to 0 except the first one. So our goal again is to somehow transform these two quantum states and create a quantum state where we should somehow be able to extract R. And how we're going to do this? We're going to apply transform in a transformation. For transformation, Hadamard transform. Hadamard transform is formally defined by H is equal to 1 over square root of 2 times the matrix with entries 1, 1, 1, minus 1. I know that lost a lot of you here, and to make it simple, let's just try to apply Hadamard transform or zero states. First, made by one qubit. Each on zero state would have 1 over square root of 2 times 0 plus 1. If you apply it on a zero state with 2 qubits, we would have 1/2 times 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. If we applied it on a zero state made by 3 qubits, we would have 1 over square root of h times 0, 0, 0 plus 0, 0, 1 all the way up to 1, 1, 1. You actually notice some pattern, no? Whenever we apply Hadamard transform or some quantum gauge, when all the qubits are set on 0 and it has a size of n qubits, it gives all the possible states from 0 to 2 to the power of n minus 1, since 1, 1, 1 in binary just means 7, and 2 to the power of 3 minus 1 is 7, times 1 over square root of 2 to the power of n. So if you actually apply Hadamard transform on our R1, we would get the sum from 0 to 2 to the power of n minus 1, meaning all the possible states from 0 to 2 to the power of n minus 1, times 1 over square root of 2 to the power of n. So when again, the pattern that we found, right? So that's the state of our R1 now. Next, what we're going to do, we're going to try to express the quantum system, all the quantum registers in one unique quantum system. And how do we do this? We said that the quantum system is expressed by the tensor product of both registers. Even notice that we could actually 0, 0, 0, 1 could be just simplified and just be written as 1. What does tensor product mean again? Tensor product is just a fancy notation again, just mean multiplication between quantum states. What I mean by this is that if you have the state A plus the state B tensor product C, it would give A times C plus B times C. And what I mean by times is just the tensor products again. You could even notice that we could even remove the tensor product sign, again, just for more simplicity. So if you apply actually the tensor product on our sum, you could just see it as a sum times one constant, which would give then the sum of each term multiplied by that constant. The same as if you have a plus b plus c multiplied by d, you give ad plus bd plus cd. Same thing. So this is our state now. Then what we're going to try to do, we're going to apply another transformation that Shor called the U transformation. It's just a transformation that it's not really called the U transformation, but like you're going to use this transformation here. He himself defined it. How is U defined? When we apply U to some state k, we get this G times K modulo N, where G again is our random guess, and N is the number that we're trying to factor out. So we're going to try to apply U in each pair x times 1 that we have in this in the parentheses. How did Shor again define U? He defined U. So when we apply U in x transfer product with 1, he defined it as x transfer product with U applied x times on 1. And what would this give? Following our initial definition, it would give G to the power of x with little n. Since K was 1, so 1 disappeared, and it would give G times G times G x times. Then our whole quantum state now is just. So to make it even more simple, let's try to apply U on an example. Let's say we're trying to apply U on 101 times 1. We would get then 101 times 0 to the power of 5, U applied 5 times on 1. And again, following our definition, it would give 101 times G to the power of 5 modulo N. Why is it 5? Just because 101 in binary means 5 in decimal. Then our quantum state would be just the sum of x times G to the power of x modulo N. Like we could just imagine, could just see as we transform with each one in G to the power of x modulo N. So that's our quantum state now. Next, you could notice that actually we have some periodicity in our quantum state due to the modular properties, right? To make it even more clear, let's say that we applied U transformation in a stage where x is going from 0 to 7, n was equal to 26, and our random guess was equal to 3. What would this give? Should give, from again our state, 1 over square root of 8 times 0, 0, 0 with this times the 2 to the power of 0 modulo 26. 1, 2 to the power of 1, 2 to the power of 2, 3, 4, 5, 6, 7, all the way to 7. And then just calculating the powers, this would give, notice the periodicity, 13913. Again, due to the modular properties. Moreover, notice something really cool. What's the period? 1, 3, 9. The period is 3. And 3 is the first power such that 2 to the power of r was equal to 1 modulo 6. 2 to the power of 3 give us 27, and 27 modulo 6 give us 1. So if we're actually able somehow to extract the periodicity of the quantum state, we would be able to extract r such that G to the power of r would be equal to 1 modulo n. Unfortunately, we can't. However, we have something really cool called the quantum Fourier transform. What is quantum Fourier transform? It's officially defined as Q of x gives 1 over square root of n times the sum from 0 to n minus 1 times of the exponential 2 pi I x k over n times state k. Again, I lost a lot of you here, and to make it even more simple, let's just imagine it's Q of t as a black box. If you introduce the quantum state in Q of t, we would get back the frequency. However, to make it even more complicated, we don't get the frequency. We get actually the frequency times the number g. And g is the whole other number that we're going to enter into details. And remember, the frequency is equal to what? It's equal to 1 over the periodicity. So this is equal to 1 over the period times t. What's the period? It's r. This is equal to 1 over r times t. So actually, we found 1 over r times t. However, if we can measure the quantum state and we find use quantum Fourier transform and we find 1 over r times g, we wouldn't find it as a fraction. We'd probably find it as a floating point, as a decimal number. Let's say, for example, that I found 0.312. We can extract r from this. And again, we have another cool algorithm that we can use here. That's called the continuous fraction algorithm. How it does work? Take 0.312, for example. Make it as a fraction. It's equal to 0 plus 312 over 1,000. Inverse the fraction, and then simplify this expression. You give 1 over 3 plus 8 over 39. Then repeat the same process until you get one in the numerator. And then notice that each line in the fractions would give us a better approximation for r. For the first one, it should be equal to 1 over 3, and the r will be equal to 3. For the second one, to be equal to 4 over 13, it will be equal to r over, and r will be equal to 13. And in the third one, this will be equal to 5 over 16, and r will be equal to 16. And we're going to choose which r. We have to follow two conditions. One, it should trivially be less than n. And second, it should be an even number. Because as we said before, if it's an odd number, our half will be a whole number. So in our example, r would be 16. And that's officially the end of our quantum subroutine. And moreover, an official end for our algorithm. During this talk, you had the whole journey which was algorithm. You had the whole story with it. And I'm sure that you have a lot of questions in mind now. And one of them would be, okay, now I showed you how this was algorithm work without mistakes. I showed that it's actually we're able to do this was algorithm basically. And again, the same question comes. So how is RSA strong? And why are we still using RSA? We still use RSA, and why are we doing it? Actually, again, I lied a bit and we didn't. Why? Because we're assuming that we have a quantum computer that is able to run Shor's algorithm, and we don't. Shor's algorithm is at least 20 million physical qubits to run. And currently, the main actually in the quantum computation is IBM, and they're aiming for 1,121 qubits soon, which is way further from our 20 million qubits. However, the day we're going to be able to build such a computer, we'll definitely be able to break RSA. So the right question to ask is not if we're going to be able to, but when. This was the Qubit and Shor's algorithm. Thanks to Ahmed for organizing the event. Thank you all for being here. Thank you very much.
It was a really nice talk. I want to know if we have questions for the speaker. So, Arne, please.
So I have a few questions. First thing is about the last remark that you made, that IBM is currently going somewhere around in hundreds and thousands of qubits, right? But recently, Microsoft also released their own quantum microchip, which claims to have millions of qubits. Yeah, millions of qubits in small volume as well. So let's see how that turns out.
Hopefully, this one's.
Hopefully.
Yeah, because in RSA.
Yeah, because they claim that it's like over million qubits.
They claim the only one that we really saw is the IBM one.
Yeah, no, they released a paper that does prove it, but we haven't gotten it commercialized. That's
Yeah.
okay. Now we see how that goes. The second thing is, my first question was why that R should not be even. That you answer it later. Why should it always be even? You answer it later. But now my question is, why not odd? Because like the thing is, when you could you go back to the place where you factorize it? Because the problem is not with R being odd. The problem is with R being prime. Because if it is not prime, if it is still a composite number, and even if it is odd, you can still factorize it into two. So some express, yeah, here. Yeah, here in this expression, right? GR minus 1 is congruent to 0 mod n. The problem is not R being odd, but the problem is R being prime. If it is not odd, this function is still factorizable.
No, but if it's odd,
Yeah.
our half will be an integer, and this for our half will be an integer.
And we don't necessarily need to do it R half, because we can just do x cubed minus 1, and that's still factorizable into 2 factors.
I feel like this is a question for Peter Shor.
Yes, but the
Can you ask
that one, right?
Can you ask just again?
So take x cubed minus 1, right? You can factorize this into x minus 1, x squared plus x plus 1. And this is still 2 integers. And it factorizes into 2 integers. It's not that the problem that R being odd, but it's R being prime, bigger prime in a sense. So I think we can make our algorithm much more efficient, or like not efficient, but we don't necessarily need to look at R that's just even. It's just the problem that R is not prime.
But
Like we need to have a multiple of 3.
But the expression
No, does not necessarily
the
need to.
expression assumes that GR minus 1 is a prime, right? Like this expression, or you're saying that this will be a prime.
Prime, no, co-prime with respect to n.
Co-prime with respect to n.
And that does, should not matter.
So like when you factorize it like x cubed minus 1 or like some polynomial of x to the n minus 1 expression where it's odd, like how can you guarantee that the second expression that you factor is also going to be good?
Yeah, exactly. That's why R should be not prime.
So I hope this answers your questions.
Or it's just a
Maybe you can cooperate with Ahmed
Yeah.
on the next quantum algorithm.
So yeah, that was my question. So slight modification because I think it should still work.
So Mr. Shor.
Very good. Very good.
Then we will have like predicted multiplier g minus 1.
Yeah.
And probably this is not the one we want. So we need the second, which is this geometric progression, which is huge.
That's very interesting.
Fair, yeah.
So let's see if I think Camila has a question.
Is quantum computing the only way, so to say, to run Shor's algorithm, or
No, you can write on a classical computer, but it will take too much time. Like the whole point is about finding R, and the classical computer can find R in the same way that a quantum computer does.
So for what exactly would it help us right now, like to lay the foundations, to raise sort of like awareness that our same
Yes.
might be jeopardy?
So for now, like a lot of scientists are so. For example, I don't know exactly what company, but they did like sort of tournament. They called all computer scientists. So they told them, okay, so build like an encryption method. There is quantum resistance. That's how we call it. Basically, even if we are able to build a quantum computer, we shouldn't be able to break it. That's like people now are trying to find such encryption methods. Because actually, a lot of quantum, encryption methods relies on, I would say, numbers. I don't know if you get what I mean. Like combination of numbers, one numbers, you get this, you factor out. And using the quantum computers, you could do this calculation way faster than a classical computer, which then would break it.
Only use quantum computing when it comes to this, or there are some aspects, or to some degree, that you need classical computing to run this algorithm? Like
Yeah. So, for example, all the steps can be run in a classical computer, except the step of finding R. Like you can pick a random number g in a classical computer. You can factor out g to the power of r minus 1 in a classical computer. You can apply Euclid's algorithm in a classical computer. And even like in the quantum subroutine, we had some algorithms. For example, the continuous fraction algorithm. At the point where you find what's equal to g over r, you could move to a classical computer and learn continuous fraction algorithm to find what's r. So the whole thing of finding, like, I would say, g over r.
Very good. I think Professor Ovsyannikov had a question.
I have a question.
Yes, sir.
Do you have a device that makes Adamar transformation? So how can we do it?
We need a quantum computer.
So with this Adamar transformation, if you can perform it on some electronic system, for example, you make a measurement on electronic system. Then after the measurement, it's in some well-defined state. So after the measurement, the system is now in one of these states exactly. And then if you apply this Adamar transformation, then you put the system in which all probabilities are the same.
Yes.
Then you will get very efficient and very cheap random numbers generator.
Yes. Yes, actually.
Okay, so more questions by Noah.
Yeah, could you go to that one matrix transformation you had? They denoted H.
Yeah, Adamar.
LMR. Yeah, this transformation. You chose to use the matrix representation in Hilbert space, and I was curious. I won't go through it. There's also vector representations of your pets, so your 0 and 1 states. Yeah, like these guys. How
These are not vector representations. I mean,
these are these are cats in Hilbert space, but in this case we've used just a usual matrix, right? How is it that this applies to the cats? Like, or do you know?
so a quantum gate. So basically, how do we build a quantum transformation? If I remember, because like I didn't spend too much time on it, to be honest. So basically, it's same as gates. Basically, you know, XOR gates the same. Like we have quite the same for quantum computers, and each quantum gate that you make is actually I would say the more accurate name would be a Hadamard's gate. And basically, each gate could be presented either in matrix form or in a hat form, basically. And there was a way to converge that I don't remember, to be honest.
It's okay. It's okay.
But there There is Helmut in my research paper. I think I wrote the Helmut transform in this form basically.
Yeah. So
yeah. Moreover, if you want to know more about details, like I'm probably gonna publish my official research paper in this week. I think like maybe tomorrow. If anyone want to read it, it will be available.
Yeah. So additionally to the talks, we also asked speakers to write some sort of paper / article to explain their ideas that they're presenting in much more detail. Now, another question.
Yeah, can you go over again how the electron superposition points like different qubits, I think.
This. What's the question?
Like explain that one more time.
Okay, sure. So basically, like before, so in our classical computer, is a kilo computer, microcomputer, we present bits or a 0 or 1 state in the presence or the absence of electricity. So we had to find another way to create states, and some way that we could also stay in between. And the way that we found is using electrons. So each electron has a property that we call the spin. They say an arrow that is pointing somewhere. Yeah. If the arrow is pointing down, we say then that's it's in a 0 state. And if it's pointing up, we say then that it's in a 1 state. And if it's pointing somewhere in between, we say then that it's a state between 0 and 1, basically.
I'm not sure if it's clear or not.
Oh no, I can.
This is the arrow. This is the pointer. This is the pointer.
Okay, my question, I don't know if it's going to be in school. This like, how does that work? Is it like magnetic and then it goes like up, down, left to right? And if so,
if I'm not wrong, because I remember they said if it was on top, we call it maximally charged.
yeah.
It could have a relation with the magnetic charge. I'm a physicist, so
I think we have many physicists here. They can explain to you how the quantum spin works.
How's that?
Okay, let's do one more question by Shor.
I have one more question.
Sure.
An explanation of why we can't use electricity is the fact that there can only be 0 and 1. Why can't we use different amplitudes of potential to say that 0, 1, 2, 3, and so on and stuff?
Say that's not efficient enough. So complicated. And imagine you're gonna do this for each qubit.
States?
Like
What?
These states specifically?
Yeah.
Not just these states. I mean, like because you're saying that there's multiple states in between as well. Instead of using quantum computer, why can't we just have multiple amplitudes of potential, saying that this is 1, 2, 3, 0?
But okay, in actual computer and like stuff, the potential comes in discrete form, but we want it in continuous form. That's why we are using qubits. It's changing from 0, 0 to 0, 1 or in any state continuously rather than discretely. And to discretize, you need more and more intervals, which is like more and more details.
And this gives you more.
Yeah, this gives you continuous changes.
Yeah, it's more of a risk to the superposition effect. So never really 0 or 1, but it's somewhere in between. So it's expected to be on the spectrum of values between.
Think of this. Think of an electron state as a discrete random variable, where 0 and 1 are your two outputs, and then your coefficients are your probabilities in a sense. Well, the square root of your probabilities. Then think of measuring that state as measuring the state, like if it's a 1 or a 0, as sampling from this random variable.
Gotcha.
That is what it corresponds to. You get either a 0 or 1 out, but the random process behind it is correlated to this continuity.
Okay.
When measuring it, you're kind of sampling out of 0 or 1 based on these coefficients.
Okay, that makes more sense.
Yeah, all of these processes are probabilistic in nature, so it's not deterministic.
So at the end, you're getting a 0 and 1, but then the probability of that is what you're talking about.
Yeah.
Amazing. Then let's thank our speaker one more time.